Good morning, everybody. It is Friday the 13th. Whew. Oh man, scary, huh? So, real quick, before we get into the lesson, I want to do a little bit of review. And if I had you in class like I do first period, we'd do this in class, but I don't. So, real quickly, I've got y equals 3 times 2 to the x. This is an exponential function, okay? And it's called an exponential function because the exponent is the x. Okay, so what I want to do is evaluate it because I really want to take a look at the graph. So I'm going to plug in these numbers. I'm just going to use my calculator, okay? I'm just going to go 3 times 2, and I'm going to plug in negative 2, okay? Plug in negative 2 to the power of negative 2, and I get an answer of 0.75, okay? So I get a negative 2 comma 0.75, okay, and I'll do the same thing. I'll go 3 times 2 to the negative 1 power, and I get a 1.5 and a 1.5, and I'll plug in a 0. Well, 0 is easy, anything 0 power 0. So we get a point at 3 comma 0. Plug in 1, that's easy because you get 2 to the 1 power is 2. Oh, do not do this. 3 times 2, do not do that. You got a 2 to the 1 power is 2 times 3 is 6. So you do get an answer of 1 comma, oh, I did this backwards, 0, 3, my bad. It's Friday morning. Plug in 1 and I get 6. And if I plug in 2, I get 2 squared is 4 times 3 is 12. So I get 2. 12. Okay, now if I look at the graph of this function, you're going to see, and we did this last year, what we call an exponential function, okay? And it looks like this, okay? Here is 1, 2, 3. It's going to have this kind of shape, okay? Hey, Eric, they're right there. It's going to have this kind of shape here. We're going to go through 3 because that is our first value, like our y-intercept, and then it's just going to curve. It's going to have this exponential curve. We've heard that a lot in the news lately about COVID, about an exponential curve, just growing faster and faster, okay? Now, what about domain? I want to talk about domain. Domain is all real numbers because it's forever wide. X equals all real numbers. But range is a little bit tricky because what happens is it never touches. It never gets to 0 because half of a half of half, you can never get there. So the range of this, okay, is y is greater than 0. Not equal to, but greater than 0. In fact, I'm going to highlight that, okay? I'm going to highlight that. So the range that never touches, it never equals 0. So the range is greater than 0. Okay, then 16, I'm sorry, number 2. It's like a half. We're going to take half. So this is my base. Base is 1/2, and I'm not even going to plug in numbers because I just know how it's going to work. So I know that I'm going to start at a height of 16. Let me show you what this looks like. Okay, so I'm just going to go, oh, maybe 5, 10, 15, and so forth and so on. And so this one is going to have a y-intercept of 16. It's going to be right there, about there. And it's going to take half of it. So if I go and plug in 1, half of 16 is 8, right? So I'll put a coordinate there, a point there, and then half of 8 is 4, right? Just taking half of it, 4, and half 4 is 2, and then so forth and so on. So this graph looks like this, okay? And we talked again about this last year. Domain and range are the same, all real numbers. Range, it never touches, so the range again is going to be y is greater than 0, okay? So, what about this? Okay, now this is what we really want to talk about today. Okay, that's just a review of things we did last year. But what about this? Okay, I'm going to get out my calculator. I'm going to plug in these values. I'm going to go, and if you were in class, we would do this. We'll probably do this again on Monday. 1 plus 1 over 10 to the 10. Let's see what we get. Parentheses. 1 plus 1 divided by 10 to the 10th power. Probably super big, right? Oh no, 2.59? 2.5937 blah blah blah. Okay, let me plug in 100. 1 plus 1 over 100 to the 100. Okay. I'm going to do that. Parentheses 1 plus 1 divided by 100 to the 100th power. It's got to be huge, right? Oh, 2.7048. Wow. Yeah, I know what's going on, but I'm just going to keep it a secret for right now, okay? So how about 1,000? 1 plus 1 over 1,000 to the 1,000 power. So I'm just taking these numbers and I'm plugging them in for x into this function right here, okay? So, okay. Parentheses 1 plus 1 divided by 1, 2, 3 to the power of 1, 1, 2, 3, and I get an answer about, oh, 2.7169. How about 2.7? How about, you know, approximately 2.71692, blah, blah, blah. And then we'll try a million, okay? 1 plus 1 over 1 million has 6 zeros. 1, 2, 3, 4, 5, 6 to the millionth. And you'd think it'd be gigantic, wouldn't you? Well, all right, let's check that out. Parentheses 1 plus 1 divided by 1, 2, 3, 4, 5, 6 to the 1, 2, 3, 4, 5, 6. Oh, must have done something wrong because that's not right. Parentheses 1 plus 1 divided by 1, 2, 3, 4, 5, 6 to the power of 1, 2, 3, 4, 5, 6. There it is, 2.718, 2.7182, blah, blah, blah. Okay, so what's happening is you get bigger and bigger values. As you get bigger and bigger values, and if you can go to infinity, in fact, let's talk about this. If you can go to infinity, you get this thing called the number e. The number e, what? So what we're going to talk about today, we're going to talk about the number e. And number e is actually, check it out, it's on your calculator, it really is. If I look on my calculator, it is right there, and it's also right there. Okay, it's called the number e because it's called Euler's number. Okay, Euler's spelled like this. I know it's a French name, but Euler's number. So this dude, this French dude, called Mr. Euler, Rene, oh no, that's Pascal. What was his first name? I can't remember his first name. I'll remember it later. He was a French mathematician that came up with this whole thing, and that is if you can go 1 plus 1 over infinity. Now you can't go to infinity, but if you can get to infinity, to the infinity power. So as these numbers get bigger and bigger and bigger, think about this. 1 plus, this becomes really, really small. So it's 1 plus just an itty bitty bit to the infinity power. So it turns out to go and becomes the number e. That's the definition of the number e, okay? In calculus, you're going to put this little limb as n approaches infinity, but you can worry about that when you get to calculus. So if we graph this on a calculator, let's see, check it out, let's see what it looks like, okay? If we have graph y equals, so I'm going to go ahead and do it. I'm going to go, okay, y equals, let's clear that, and I'm going to go simply e to the x power. Let's see what it looks like. Graph it. Okay, now it doesn't show everything, but it is in what we call exponential growth because e is bigger than 1. So it looks like this. And it grows exponentially, okay? That's the parent function of y equals e to the x. Domain, well, it's forever wide in both directions, right? X equals all real numbers for domain, but range, it never will touch 0. It gets smaller and smaller and smaller, but never, ever, ever touches the x-axis. So as it goes along, it gets closer and closer and closer to the x-axis, but it never touches it. So the range has to be above that, above y is greater than 0. Not equal to, but greater than, okay? All right, now number 3, we can graph this, and I can actually just put it on my calculator. Okay, I can go 3, and I can go e to the x, and then subtract 2, and graph that. Okay, so what happened, hold on, yep, graph that. So if I did my trace, I don't know what that is. If I go to my trace button, it still goes through 0, 1, but it's going to go all the way down here. Okay. If I use my trace button, my calculator, let's see, trace. Now watch this. Watch this, okay? It is getting closer and closer and closer to what? The y values. Closer and closer to -2, okay? So that means we drop the whole thing down 2 because of the -2, so 1, 2. So we're going to put a thing called the horizontal asymptote. Okay, I'm going to put an imaginary line right here. This is called a horizontal asymptote, okay? We've talked about asymptotes before. They're invisible lines like boundary lines, and so my graph is going to look something like this. A little bit steeper because of the 3. Now what happens is it never touches this line. You can see it. You can keep going. If you look at the y values, it's just never going to. I've got -2.9999. If I keep going, it's keep going. It's going to get closer and closer to -2, but it'll never reach -2. Never reach -2. This is y equals -2. Okay. So domain, yeah, it's forever wide. It goes forever in both directions because as it's going up, it's still going over. So my domain is still going to be x is equal to all real numbers. Okay, but the range, well, look at it. Here's my. It never is going to touch -2. So my range is going to be a y is greater than -2. You see this graph, it's going to level out at -2 without touching -2, okay? So that's my horizontal asymptote and also my range. Okay, number 2. Okay, so number 2, let's see, y equals 2. Let's graph that one, okay? So y equals, let's clear that. I'm going to go y equals 2. I'm going to go e to the, and I'm going to go -0.2x, and then I'm going to graph that. Oh, I might need to get my window back the way it was, which I will, but this one looks like it's decayed. It looks like it's going down, not growth, but decay. So let me go back, excuse me, to my window. Okay, I want a better window. Let's go -2 to 2, and the y's can go all the way from -5. Let's go to maybe 5. Okay, let's graph that. There you go. Here it comes. So it goes through at 2, and that makes sense that it would go through 2 because it's kind of like a y-intercept. Okay, and it's going to look like this. And I believe if I do my trace button, let me do a better window. Go to maybe 15, graph. You'll see it dives down, but it's never ever going to touch 0. It looks like it does, but it never touches it. It goes closer and closer to that. So I'm going to have a horizontal asymptote again at 0. Okay, and that's the parent function. So here's my horizontal asymptote at y equals 0. There's my horizontal asymptote. So my range is going to be a y equals, or I'm sorry, y is greater than 0. Now, if we want to change it to this form right here, all we have to do is figure out what e to the -0.2 is, because then we can replace this value as a 1 plus r. So we're just going to take it out of the e range. So let's figure out what is e to the -0.02. So let's go, okay, clear. All right, so I want to put it in this form. Not e, but 1 plus r, normal form. So my calculator, if I go, okay, what is, hold on, e to the -0.2, and I get an answer of about 0.8, let's round it to 0.82, okay? So this answer is 0.82. Well, that's the same thing as, if if I wanted to find out 1 plus, so it's really 1 minus, okay, hold on, let's see, 0.82. 0.82 is equal to 0.82 is equal to 1 minus point, let's see, what's 100 minus 82? I think it's 18.18. Okay, aren't these numbers the same? So I'm going to rewrite this as, let's see, I'll squeeze it in here. Y equals, we started with 2 to the 1 minus 0.18 to the x. Okay, and these are the same graphs, same number, same graphs. Okay, we'll talk about this more in class. Hey, let me turn the page. Okay, now E is just like x. Okay, so when you look at your assignments today, think about E as x. This is like E times E times E times E times another E times E times E. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Well, it's really like E to the 10th. Boom, done. Why did I do all that? To show you, because that was such a waste of my time. But let's look at 3. Since I ran out of room for 3, because I wrote all of this, I'll do 3, squeeze it in here. Well, I got to remember, the cube goes to both. So I'm going to have a 3 cubed e to the 15, because I had an exponent to an exponent and multiplied exponent. 3 to the third, let's see, that's 3 times 3 times 3, right? 3 to the third is 3 times 3 times 3, which is 27 e to the 15, okay? Now, next example, okay? Well, just do these. We treat them like x's. 12 divided by 4, 12 divided by 4, that's easy. That's just 3. 6 of these e's cancel 6 of these e's. Left 6 of these cancel 6 of these. I'm left with 2 of these, and then on the bottom e squared, okay? Now, one place we use e is on a thing called continuous growth. E we're going to use for anything that grows continuously, okay? We're going to use e for anything that grows continuously, okay? So we need the number, or the base e for anything that grows continuous. So we would have a formula, okay, here's our formula. We're going to have our amount over time is equal to p, which is our principal. We plug in e to the RT. Okay, some people call that the PERT formula, but that is the formula for something that grows continuously, okay? Amount over time. Now, P is what you plug in, the amount you start with. E is our E number. R is our interest rate, okay? And T is time, okay? So, let's take a look at example 4. So, Keegan has $4,000 to invest. The first bank will give her 4% compounded quarterly. Now, that's different. Compounded quarterly doesn't mean continuously, but 4 times a year. Okay, we'll use a formula up here. I'll show you that formula. But first, let's go back to E, okay? And a second bank will give her continuous interest. That means they're giving her interest continuously all the time. So we ought to be able to make more money here. So let's see how this works. All right, 4% is the same as, right, 0.04. So 0.04 is my interest rate for 5 years, so T equals 5. And I'm going to plug in 4,000. All right, this is not hard. I just have to use my calculator. All right, so I'm going to say A of 5, because the amount over 5 years is equal to, that's like the question, what is the amount for 5 years? Because time is 5. P is 4,000. E, which is my number E, to the power of 0.04 times 5. Okay, and I'll show you on my calculator. And if you don't have a fancy calculator, it's really going to be hard to do this on your phone. Really hard. But hopefully you'll find something. So let me plug that into my calculator. Okay, I'm just going to go plug it in. 4,000. And then my E button, to the power of, and I'm going to go 0.04 times 5. So I plugged it into my calculator. 4,000, my E number, to the power of 4,000 times 5, because this is an exponential. Enter, answer. So at the end of 5 years, we'll have 4,000 $4,885.61. Okay, that's compounded continuously, okay? Now, if they compound it quarterly, you need a different formula. So if you only compound it 4 times a year, this is the other formula, okay? And you need to know this one. A of t, amount over time, is equal to P times parentheses 1 plus R over N to the NT power. Okay, I'm going to highlight both of these formulas so you guys can have these in your notes, okay? This is a compounded and this is a continuous, okay? Now, N is the number of times per year. So in this example, since we're going quarterly, right? In this example, N is 4. So in this example, N is 4. So let's use the formula, okay? Let's plug all this information up here. So we're going to go A of 5, right? Because we know the amount over 5 years. A of 5 is equal to P, which is the amount of money we put in. We're going to put in 4,000 into the bank. 1 plus, because I'm following the formula, 1 plus R. Now the interest rate is still 0.04, but divided by N. N is the number of times per year, divided by 4. I'll write that down in a second. To the power of N, which is 4, times my time, which is 5 years. Okay, let's write that down. N is the number of times per year. Okay, compounded. Okay, write that down. I'm just going to use my calculator now, okay? So I'm going to go use my calculator. I want you to see this. All right, I'm going to shift this up so you can see it. I'm going to type in 4,000 parentheses 1 plus 0.04 divided by 4 because it's quarterly, parentheses to the power of, well, 4 times 5 is really 20, right? Just may as well put 20 in. Boom. I get $4,880.76. So I didn't make that much more money on the other, but I did make $5 more. So on this one, we're going to have $4,880.76 in our bank account after 5 years. So obviously, if you can compound things continuously, you compound it more often so you make more money. Quarterly, okay, I still made some good money, but I only compounded it 4 times per year. Now, as you compound money, you make money on money. Okay, we'll talk again on Monday about this so you guys know what's going on. But that's all I have, and there is homework, so please do it.